All right, welcome everybody to our seminar for today at 12:30. I'm Professor Henry Yaokao. I am a geologist, and I'm very happy to present another geologist, because we've had so many biologists and chemists here, not that they're bad, but I'm super happy to have a geologist here. We have Dr. Tiffany Roberts Briggs. Correct. She is a coastal morphologist. She went to the same graduate program as I did, University of South Florida, Go Bulls. And she will present to us, the topic today is, let's see, it's about, basically in a nutshell, it's about how your coast changes through erosion, different types of weather patterns that affect your coast and how it looks like, and how over time, nothing really stays the same. So without further ado, Briggs.
Thank you. Good afternoon. So I'm going to be talking to you about storm-induced coastal morphodynamics. So we live pretty close to the coast. I'm up at Florida Atlantic University, a little bit closer to the coast, but where we are here is in real close proximity, so I'm sure most of you know, because of our proximity, that the coast is dynamic, that it often changes from time to time that you visit the beach. Ooh, wrong button. A lot of people live near the coast, not just us. We can look right down here. This dark blue color is indicative of a real high population density in the coast across the U.S. Right, you can see these different colors where the dark blue is concentrated. That's a high population of people living near the coast. Palm Beach, Broward, Miami-Dade. We're in those high density coastal counties. So we're living near the coast. The coast changes quite a bit. Changes are from humans building structures, coastal engineering structures to help slow down coastal changes. Storms cause coastal change, often at real short events. And we've all heard that sea level is rising. This is a change that's happening on the coast at a longer term scale. But what I'm going to talk to you today about are storm changes on the coast. And this is important because we live close. A lot of people live close to the coast. So understanding how these different factors influence coastal change is part of what I do. It's part of coastal morphodynamics. So coastal morphodynamics is basically looking at the interplay of a couple of different processes. Sediment movement of physical processes that are called hydrodynamics, which are waves, tides, and currents, and the actual morphology change itself. So the term dynamics suggests that this is moving and changing quite a bit. So you have waves, tides, and currents that are pushing sand around on the coast, and as that sand shifts around, it changes the shape of the coast. And then as that shape changes, it can actually in turn feed back into how the waves, tides, and currents are moving the sand. So it's a bit of a feedback loop. There's other processes that go into this, the geology, things like sea level rise, even humans. But what I'm going to focus on and talk to you today are these three processes of coastal morphodynamics. So when storms impact a coast, it changes the sort of typical or fair weather morphodynamics of a coast. Waves and currents tend to pick up speed, which then can pick up more sediment, which can cause a more rapid morphologic change along the coast. So when I'm talking about morphologic change, this is an example of a beach profile. So you're basically slicing the beach in half. So here you have a dune and you're moving out towards the water line. So if I can walk over here so I can point a little better. Okay, so this is a really classic beach profile. Here you have what's called a berm. This is what you would see as the dry beach where you go and you put your towel down. Okay, so some of this sand can get shifted offshore during storm events. and it forms nearshore sandbars. And then maybe during fair weather or post-storm conditions, the sand gets pushed back up on the beach. And this is a cycle, meaning that this is something that happens along coasts in a predictable manner where you have a built-up, what we call berm-type profiles. Some storm hits, moves the sand offshore in the form of a sandbar, and then that sand subsequently will move back onshore, and it continues back and forth. There are other types of profile cycles. This is an example of beach profiles on the west coast of Florida. And so in this case, you don't have the same built-up berm and deflated berm from storm processes, but rather a migrating sandbar offshore. So when a storm comes, it pushes the sandbar further offshore, and then subsequently that sandbar will move back onshore. Another example of this type of profile cycle, this is from the New England coast up in Delaware. So here we see that built-up beach berm again, but when storms impact this area, the sand moves offshore, but rather than forming a sandbar, it just sort of deposits as a little thin veneer of sediment in the near shore, which then can subsequently get pushed back up on the beach and recover the berm. And so this is an important cycle to understand, because if you don't have this recovery process, you don't have a beach. So when you have another storm that comes in, if there's not time for that beach to recover, you start to have dune erosion or impacts to local infrastructure. So a lot of people pay a lot of attention to understanding how the beach changes and attempting to create these morphologic models. So again, these beaches are impacted by storms, and locally the impacts can vary according to storm characteristics. So I'm talking about low pressure storms, tropical storms, and cold fronts. The different storm characteristics will determine the type of beach change or the extent of beach erosion. So the magnitude of the storm, how big is the storm, how fast is the storm moving, what's the central pressure, right? How fast are the winds within that storm, even which side of the storm you're on. Again, we all live in Florida, so hopefully we're a little cognizant of what hurricanes can do. The right side's the wrong side. We don't want to be on that side. Certainly will cause more coastal impact. But other local variability can be induced by the sediment properties. So I know a lot of you aren't geologists. So this up here is gravel-sized particles, the bigger stuff. In Florida, actually shells would fall into this size class of sediments. This is sand here beneath. Right? So different sediment properties can influence a beach, not only the size itself, but how similar those sizes are to one another. We call this sorting. Right? So there may be a big range of sizes, or all the sediment may be very similar. And this is important because it will behave differently within the coastal zone. And one of those different behaviors are what's called fall speed. So this is basically how fast sediment that's being entrained within the water column will fall back down. So that's integral to processes of erosion and accretion, sand moving offshore and onshore respectively. So we think about tropical storms and hurricanes as primary storms, but cold fronts actually can cause a lot of change. They're very predictable. We get them every winter. A lot of coasts get these cold fronts, and so these are both really important storms to understand their impact. Here's a quick time series of actually a hybrid storm that impacted the New England coast. This was the remnants of Hurricane Norida and a nor'easter that collided in 2009, so kind of like Superstorm Sandy, but a little bit smaller scale. So you can see here the water is getting pushed up on land, the wave is crashing into the dunes and causing dune erosion. This is just an image taken 2 days apart to give you an idea of how these cold fronts can change the beach. Right, so here we have a nice wide beach. This building is this same building. 2 days later, the beach is gone. Right, and this was a cold front, a strong cold front. So this is part of why it's important to kind of understand how coastlines are changing, because if you had another cold front that came and impacted the area immediately, right, these buildings are definitely at risk of receiving more damage. And so the last part of the coastal morphodynamics is the sediment transport that is causing those morphology changes. And one of the ways that we can try to predict the morphology change that results from sediment transport is by a relationship that's referred to as the Dean number. Basically, it's taking the fall speed, this little omega here, and correlating it with wave height and wave period. So waves move in this sort of circular orbit. And so the idea of the fall speed is if the sediment is heavier than half of that orbital, that it'll fall out of suspension and move onshore. If it's lighter or smaller, as that wave orbital drifts back offshore, that sediment will also be pushed offshore. So this is a relationship of predicting onshore and offshore transport according to how large or heavy that sediment is. Right? So sediment transport, just don't get all freaked out by the little variables. It's just sort of to show you the relationship. This is the amount of sediment that's moving in the cross shore. Here is what's resulting in morphologic change. Okay, so that's sort of the background on coastal morphodynamics, and hopefully I've convinced you that this is an important topic, that there's validity and motivation for trying to understand how the coastline is changing. So next I'm going to talk to you about a couple of case studies that looks at coastal morphodynamics. First, we'll look at a norte in Mexico. So norte in Mexico is basically what we would equate to as a cold front or a nor'easter. And then I'll bring you back close to home and talk a little bit about some of the recent cold front studies that we've been conducting at FAU and some other storm studies like Tropical Storm Erika. And then I'll briefly touch on some of the planned summer research and give you a summary of the things that we've talked about today. Okay, so here we are, Broward College, South Campus. Right, and this is the area that I'm going to be talking to you about first. It's a beach in Sisal, Mexico. So Sisal is located on the northwest Yucatan Peninsula. The environment's very similar to what we have in Florida. They have lagoon-backed barrier islands. Much of their coast is considered a sandy coast, like ours. One difference is that they have a much, much wider continental shelf than we do over here in southeast Florida. And if we zoom in on the beach, right, this looks somewhat similar. Their sandy barrier island beach. This area is driven primarily by afternoon sea breezes, but they're also impacted by these nortes. And so in 2014, I participated in a large multi-institutional collaboration to study and evaluate the effects of not only the afternoon sea breezes that are considered the typical conditions, but also norte impact. So as you know, living in Florida, we can somewhat predict that we're going to have cold fronts every few weeks, and so we went out in late March and knew that if we just stayed there long enough that we would get a cold front. So that's what happened. This is our little equipment house here. We had a trailer housing all of our sensors. Put out a couple of cross-shore arrays. I'll show you some images of that in a minute to measure the local hydrodynamics. Surveyed cross-shore to capture the morphology. And then we also analyzed the sediment transport. So this is just to give you an idea of the conditions in Sisal. Again, it's a sea breeze dominated environment. So this red line is showing you wind speed, and you can see this wind speed is going up and down, right? Almost daily. So that's the afternoon sea breeze that kicks up. It's very calm in the morning, and then you have the winds pick up, causing the sea breeze. So wind speeds are around 10 meters per second or so in these events. And then here you can see the wind speed kicks up much higher. That's the norte, right? And so here we have much higher wind speeds exceeding 12 meters per second. The area is considered to be microtidal. What that means is that the tidal range is really small, the water level is not changing drastically, which is helpful if you study coastal morphodynamics, because you can put your sensors and not have to change them too much with the tides. And the sediment in the area is characterized as a poorly sorted fine to medium sand. Okay, so here's an image of beautiful Seaside Beach in the morning, no sea breeze, no waves, right? So this is our instrument array. We're out there, very calm conditions. This is a wave height measured throughout our study period. So this is showing you what it looks like when the waves are almost nil or non-existent, right? So less than a meter high. A meter is about just over 3 feet. This is what it looks like during a norte. Much different, right? So this is the sort of fair weather conditions. Here's our norte conditions. And if you look at the wave height up here, right, now we're up to a meter of near shore wave heights, right? A lot higher than these small amplitude waves that typically characterize the environment. And so this is what I'm going to be focusing on talking to you about today, is the sediment transport that's happening as those waves kick up from those higher winds coming down from the norte. So to do this, we put out 3 cross-shore arrays. They're these large aluminum frames that we attached our instruments to. Right, so if you look here, you can see some of these instruments on the aluminum frame, measuring waves, tides, currents. We actually put some sensors offshore to measure sediment transport offshore. This isn't to sort of be too confusing, but this gives you an idea of how many sensors we had out there. We had something like 40 sensors measuring everything we could during this short time interval that we had. And I'm not going to talk to you about all the data we collected, but I am going to talk to you about the streamer traps that were put out in the near shore to measure sediment transport during the norte. So this is a streamer trap. These are little mesh bags, 63 microns in size, which basically allows water to pass through but not sediment. So these streamer traps have 3 different intervals to collect sediment transport at different elevations within the water column. So we put these out on the norte event on April 8th and then the day after as the norte was subsiding in 2 different locations. One really close to the shoreline called the lower foreshore, so it's still in the water as the swash kind of moves back and forth, and another at what's called a beach step. Basically, waves will sometimes plunge close to the shoreline and cause a little divot that looks like a step. So these are our 2 locations. We put these out every 3 hours for 24 hours, which doesn't sound too impressive until you think about the fact that we were out 24 hours a day. So nortes are cold, right? Cold fronts. The 2 and 4 a.m. deployments were not that fun. It's dark, it's freezing, the winds are kicking up everywhere. But got some great data. Right? So we have a full day of streamer trap measurements. They were placed facing offshore. So these streamer traps were capturing sediment that's moving onshore sediment transport. And again, it's at these 3 elevations within the water column. So I have a little schematic here. Bed load transport is basically sediment that's rolling along the bottom, the substrate, or jumping, saltating. Oftentimes this tends to be the larger fraction of sediment. Lighter sediments can get pushed up into the water column. So this is what's called suspended load. Right? So this is the sediment that we would try to determine the fall speed. Right? This is the stuff that's getting kicked up in the water column, and we want to know how heavy it is and how fast it's going to fall. And that's supposed to determine whether we're going to have onshore or offshore transport. We also looked at sediment carried within the wave, and I'm not going to talk about that today. So this is what the streamer trap deployments looked like. Again, you have these 2 pipes and your mesh bags here facing offshore. We held them out there for about a minute and then brought them back on shore, captured the sediment, brought it back to the lab, weighed it, put them through a sediment analysis to determine the distribution of grain sizes, the mean grain size, the sorting within the sediment. And so this is some of the results from these streamer trap measurements. What you're looking at is the total weight that was captured within that 60-second interval at I'm giving you 6-hour increments here, so 3. So our 24-hour period from 11:30 till 11, and then we actually had a streamer trap measurement after the Norte passed to look at the difference in transport with recovery. 2 locations, the lower foreshore, and that's that yellow dot, and the beach dot, that green dot. And again, bed load and suspended load transport. So the lower foreshore bed load, right, quantity that's measured was much larger than what we measured at the beach depth. Right, so here we can see it peaks at, actually coinciding with the peak of the storm, the highest waves that were measured, and then it starts to decrease over time at the lower foreshore. At the beach depth, there's not the same relationship. We do see a higher quantity moving at the peak of the storm. There's some variability as the storm energy is subsiding. The suspended load at the foreshore is also larger, right, relatively larger than the suspended load at the beach depth. Neither one really shows any type of pattern with time or storm intensity. Right, so again, this is the onshore transport that was measured in these streamer traps. So how does this relate to beach morphology? So this is a beach profile similar to the conceptual models I showed you in the beginning. You have elevation with distance, looking at the beach as if it's sliced in half. So the blue line is the beach profile that was measured before the Norte. During the Norte, the conditions were not conducive for us to actually go out into the water with the equipment that we were using to survey, so skip that day, and then we have the post-Norte profile shown in red, right, and then one more day shown there in purple. So looking at these changes, we can see that right next to this lower foreshore streamer trap, right, the shoreline eroded. This 0 meter you can think of as mean sea level. So between the 7th and the 9th, we have erosion at the shoreline, right? But deposition just up on the beach, and what we call the upper foreshore, and actually deposition out at the beach depth. So this was the other streamer trap location. So if we go back and look at the sediment quantity that was measured in these streamer traps, the 2 locations, and try to correlate that to the beach morphology, right here, at the lower foreshore, we had a large quantity of bed load transported sediment, right, moving onshore. We see erosion right at the shoreline. So that sediment actually pushed all the way up onto the upper foreshore and deposited here. Right? So it looks like a large amount of onshore directed sediment transport was occurring during this Norte, causing beach accretion. If we look at the beach depth, right, so this here, you have a much smaller amount of onshore sediment transport that's occurring at this location. But there was accretion here, right? So if you look offshore, it doesn't look like too many changes here. Right, so sediment's coming from somewhere and depositing at this beach depth. Right, so it might be that you have sediment that is part of that shoreline erosion moving offshore. It could also be that sediment's coming from alongshore, right? In the coastal zone, it's not 2-dimensional. We have 3 dimensions, so sand could be moving on and offshore as well as alongshore. But certainly we see the relationship with this very large quantity of sediment at the lower foreshore pushing up onto the shore. So all of these samples were analyzed for their grain size. So the grain size distribution oftentimes is reported in mean and standard deviation, but in sediment transport, it's really helpful to look at what's called the D50. So the D50 is basically where half of the sediment is larger and half of the sediment is smaller. So it's supposed to help represent your bulk sample. So this is the D50 that was measured at all these different times across the water column. So remember the streamer traps, that very top bin, this is the wave crest. This is your suspended sediment, and then down here at about 5 centimeters, that's the midpoint of the bed load trap of sediment that's moving at the bottom. And then these all the way down at 0 are the sediments that weren't moving. They were at rest, sediment samples that were taken right, next to the streamer traps, not actually contained within the streamer traps. And if you look at this distribution here, right, you can see that throughout the water column, the D50 is heterogeneous. It's not the same. So the suspended load is finer than the bed load and what's at the bottom. This is not surprising, right? We talked about the smaller grain sizes are what gets kicked up into the water column. But what was surprising is that the bed load transported sediments are not the same as the sediment that's sitting at the substrate, not moving. Okay, so here's another way of looking at these sediments. The yellow line here is the grain size of the bed load, D50, and the gray is the bottom sediments. And the bottom sediments were actually significantly coarser than what was in transport. So 1 to 3 times coarser in the lower foreshore. I jump forward and move offshore. They were even more coarse at the beach depth. And so this is important because when we think about characterizing our coastal morphodynamics, the sediment is one piece of the puzzle. And oftentimes what we do is we go out in the field, collect a sediment sample that's sitting right on the substrate at some point in the beach profile, and that's how we characterize the grain size in the environment. But that's not actually what's moving. And again, this is during energetic conditions, so the fact that the finer fraction is what's moving onshore has some implications when we think about, well, what's the resultant morphology change going to be? So another way of kind of trying to summarize this information for you, if you take the average of all of these D50s over those times, right, the bottom D50 at this lower foreshore location is medium sand, and at this beach depth we're looking at coarse sand. But what's actually moving onshore is a much finer grain size than what's sitting in these two regions. So we'll see a fining onshore. So finer stuff is actually moving onshore, coarser stuff is either sitting or moving offshore. And this goes against what a lot of us understand in terms of coastal change. We think fine grain sizes are moving offshore and coarse stuff is moving onshore. Right? Remember the D number, that's one of the predictions with the fall speed. But that's not what's happening in the bed load fraction. And even more interesting is that it's not happening during a norte, these really energetic conditions that we think all the fine stuff's going to wash offshore. It's actually not. Some of it's moving onshore as bed load transport. So if I take you back to this D number, right, the D number is based on the fall speed of the suspended sediment. But in our case, the suspended sediment was much finer than the bed load and what's sitting at the bottom. And if you plug in our suspended sediment grain size into this morphologic predictor, it's predicting erosion, right? Which is reasonable. During a norte, one might expect erosion. But that's not what we saw in CSAL. We saw a little shoreline erosion, but we actually saw deposition on the upper foreshore. And so the D number is used widely, and it's been verified in a lot of places. And there's, right, in my opinion, there's some utility to this in certain areas when you're using the fall speed. But what this study really started bringing out was that it may not always be the best morphologic predictor, looking at these fall speeds. Right? So from our experiment, one of the questions that's come out is, can we create a simple parameterization that will predict morphology change similar to what the D number does, but looking at bed load transport? So not considering the fall speed, not thinking about what's getting kicked up in the water column and moving with the wave orbitals, but what's actually moving along the bed that seems to be resulting in the beach morphology change. I don't have an answer for that yet, by the way. That's part of the beauty of science, right? It brings up questions and we have new studies. So part of this ongoing study is now happening at FAU. A group of graduate students this semester have been going out and collecting data at a very popular beach in Boca called South Beach. I went out on a cold front day, nobody wanted to sit on the beach, but here spring breakers are showing up and you can see the beach is getting a little bit more active. And so these students are going out in collecting beach profile data using what's called RTK GPS, using satellites to determine location and elevation. They're collecting sediment samples. They were estimating breaking wave height and wave period, all the things that are needed to plug into the Dean number, right? Determine if the beach is going to accrete or erode. And some of these students were also doing mini projects, a couple of which put streamer traps out to see what type of sediments moving within the area. So this is some of the results from this class this year. This is wind speed in the area. And this is beach profile data that was collected with the RTK GPS. All right, so you can see this is pretty recent stuff, just a couple of weeks ago. So the first day that we went out on February 5th, this is the orange line here, was actually a cold front day. It was pretty energetic. I think my students went home and cursed me that day and were like, what are we doing out here? This is going to be crazy. But it was great because we got profile data as the storm's happening. And so if you look at the profiles collected about a week later, you can see that there was erosion right from that cold front. On the 5th, this is the D50 at the dune toe, what we call the berm crest, where you see this little change in elevation, and then right around the swash zone at the shoreline, different grain sizes, 0.29, 0.35, 0.35, right? So it's getting slightly coarser as you move offshore. A couple of more cold fronts happening in between these two time intervals, right? So then we look at the change between the green and the purple line. And despite these two cold fronts going by, we see accretion at the shoreline, right? Another couple of cold fronts occur, and then we go out on the 14th. From the purple line to the blue line, we see even more accretion, right? This line's higher than that line. It means the beach is gaining sand, right? If we look at the grain size from March 14th, right? No change up here, that's not surprising. At the berm crest, we see that it's getting slightly finer. And down at the shoreline, it's getting slightly finer, right? So we go from 35 millimeters here to 0.31, 35 to 0.30, right? So there seems to be fining in the cross-shore distribution of sediments as we see accretion along the foreshore following these cold fronts. This is very similar to what we saw in Sea-Sal. Right? So one of the questions that I have for the students is, well, how do we know that this is onshore transport? Right? So in Sea-Sal, we're saying, oh, we think it's onshore transport because of this streamer traps that captured onshore transport, but certainly could be from sediments coming along shore. So a group of students at a site just north of here decided to test this hypothesis and determine whether or not the sediment's moving cross-shore, or the finer sediments are moving cross-shore or along-shore. So you're looking at a very similar plot. This is your beach profile, right? From the start of their class experiment on the 8th, right? Here are the grain sizes up here at the berm crest and down at the shoreline. Similar trend of getting a little bit coarser as you move offshore. And then on March 14th, which was their last class data collection, up here again, no change, not too surprising, but we see that the sediment is getting finer down here at the shoreline, where we also see accretion occurring, right? From the orange to the blue, we're gaining sand. And so one of the groups put streamer traps out, and instead of facing offshore to get the onshore transport, they turned, right, and faced north or south, so a longshore direction. So this is their beach, this would be the cross shore, and they collected data of sediment that was moving alongshore. So on the 8th, it was still somewhat energetic conditions from this cold front, so we have sediment moving to the north. Here's the grain size, 0.18. Tiny bit of sediment moving south, also 0.18. Right, so that's actually almost the same, right, as the berm crest sediment, slightly finer than what was at the shoreline. If we look at what's moving on the 14th, right, here the direction has switched. This happens on the coastlines. This wasn't during the Norte. but rather fair weather conditions along our coast. Most sediment, the net drift is to the south, so here we have more sediment moving south. In this case, the D50 is 0.21, and the tiny little bit that's moving north is 0.2. Right? And so this is coarser than what's measured at the shoreline. So if we look at the change from 0.2 to 0.18 at the shoreline, right, there's a fining, but if we look at what's moving along shore, right, this is the same here, but it's actually coarser on the day that we took these measurements. And so preliminary data is suggesting that what's moving along shore may actually either be consistent with the in-situ grain size or coarser. Right, so this all feeds back into, well, maybe the stuff that's moving on shore is actually finer. Right, maybe the bed load, so again, this is bed load flux from the streamer trap, same deal we did in CSAL, we did here. And the sediments are a little bit coarser. So this is being integrated into graduate student research. One of my students, Will Warren, is going out and collecting more data, time series, cross-shore and along-shore transport quantities to get the sediment flux, specifically, again, in the bed load to determine along-shore sediments are the same grain size as what's moving cross-shore. So this was actually just a couple of days ago. These guys were out collecting this data in Delray Beach. Okay, so those are cold fronts. Those are predictable. They can do a lot of coastal change, a lot of damage. Again, showing you the images from the nor'easter in the New England coast. Tropical storms and hurricanes, lucky for us, don't happen as frequently. But last year we did have a somewhat close call, the tropical storm Erika. Here's Erika's track. We thought for a second it was going to be coming very, very close to our coast. And so what this did was it expedited a planned study to try to monitor coastal change using remote sensing techniques. In this case, using a drone. So this is not your creepy neighbor's drone. This is like a very large, high-tech drone that has automatic navigation, has a very high-resolution camera down to a centimeter scale that can create very, very accurate 2D and 3D maps of the coastline. Right? So you can create point clouds and digital surface models, scaled ortho photos, feature maps, you name it. And so this is a project that I'm working on in collaboration with our resident remote sensing and GIS experts. I'm contributing the coastal morphology expertise. And this is actually going to be integrated into a PhD study by James Gammett Clark. And so what he is trying to do is see if this remote sensing technique can accurately map these coastal changes that are measured at a sort of, when you go out and collect beach profiles, it's not nearly as dense as this drone data can collect. So I'm going out and collecting beach profiles, and we're going to compare the data that's collected with the drone. And so we tried to do this for Tropical Storm Erika. I have a little video here of this drone landing. Let's see if it plays. So see if you can see it coming in. You'll see a little black dot right here. So this is as the drone is finishing its flight, coming in, and lands on the beach. Okay, so kind of cool, techie stuff there. This is the drone launcher. So we put the drone on this like slingshot launcher. It goes up in the air, flies around, collects its data, and then you just saw what it looks like when it lands. So we went out before Tropical Storm Erika on August 29th. And then again, after Erika passed through, even though we did not have the direct hit that we were worried about, on September 3rd. There were still actually substantial coastal changes that occurred from Tropical Storm Erika. So these are some of the images that we got back from the drone flight. This is pre-Erika conditions in the South Boca area. Right, so you can see the rack line from the waves moving up. And then the post-Erika photo, this little pink thing here, right, is a rock outcrop at the shoreline. So all the sediment that had been covering this rock outcrop was washed away as a result of this storm. Right, so not a huge storm, but still causing some coastal change. Here's another image from the drone flight, pre and post Erika in northern Boca. So if you look at the first photo, you have a morphologic feature that we call a tombolo, right? So sediments kind of coming out with this little rock feature here, right? Shaping the shoreline in such a way. And then the post Erika, that tombolo is kind of washed away, and you have what we call a salient. You still have a little perturbation in the shoreline, but it's not coming all the way out to that rock structure. So all of this sediment here was eroded, right? If you look at the rock structure, it's much more visible now post Erika. So again, what little bit of sediments may have been covering that are now uncovered this rock. And so for the biologists in here, right, this is hard bottom. We care about this, but this is starting to show how quickly these hard bottoms can become exposed or covered with a very small storm, small coastal transport morphology changes. I have one more video for you just to kind of show you, started on that, next. What the point clouds look like. So this is a digital surface map flying from South Boca to North Boca. Right, so these are some of the types of images that come from this drone flight. This is the rock outcrop we just flew over, right, getting back down onto the beach. You can see the dunes up here. Right, and so the idea is, flying this drone, we're able to map the coast, and we can do this in such a really dense fashion, and we're hoping to determine whether or not this is accurate enough to replace our traditional cross-shore RTK beach profiles that I was showing you. So some of the future work, so that was Tropical Storm Erika. We're using the same technology to monitor a beach nourishment project that just started about a week ago in the Boca area. Right? So beach nourishment, they take sand from offshore, pump it onshore to make your beach wider, right? Have storm protection, create habitat, etc. So we've been going out and we flew a pre-nourishment drone flight. We collected profile data, all these little green dots here. We'll be out tomorrow morning. They've started pumping, so we're going to go and fly the drone again and capture the changes as they're pumping sand onto the beach and collect the beach profile data again. And this is actually going to be integrated into another one of my master's students who's going to look and see at profile equilibration from this project, and that's also going to be integrated into James's larger PhD study. And then last, so I don't know if you guys know this, but we've been in what's called a super El Nino influencing our weather. And so there is some probability that following these super El Ninos, we can have a La Nina summer. And so why we care about that is that La Nina summers are known to coincide with a higher probability of storm activity in the Atlantic, right? Uh-oh for us. So some of the summer research is going to be looking at whether or not these storms impact our area, how they change the coast, and how this correlates to sea turtles. So again, for the biologists in here, we're looking at working with one of the professors in biology at FAU to look at how the profile changes and how that influences turtle nests. So this is an example of an exposed turtle nest. So that's a direct implication of coastal erosion, but other implications are if your beach is eroding, the water can get up much further on the beach where some of these turtles nest. So loggerheads are nesting kind of in the middle of the beach. If your beach is eroded, water can inundate their nests and potentially drown them. Or it reduces the oxygen that they need during their development. Even green turtles that are nesting further back on the beach, there may be some implications if we have this La Nina summer and we have substantial erosion, so not only from washout, but also from inundation of the nests. And so this is going to be also part of a PhD student working with me. She's going to look at the morphologic impacts, and that's being integrated into one of Dr. Milton's graduate students who is looking at the embryo development and timing of potential inundation events for these sea turtles. So in summary, right, I've talked to you a little bit about the fact that beach morphology changes. Sometimes it's predictable, but if it is, we want to know what those changes are and how we can predict them. So this is central to my research at FAU. What I'm interested in is trying to determine what's that relationship between the sand that's moving around and those morphology changes, and whether or not we can predict the morphology changes. So from the Sea-South study, and actually from preliminary research in Boca, we're seeing that the beach profile is recovering very rapidly from these cold fronts. We just see onshore transport rather than erosion by the time we're taking these profile measurements, right? And a lot of this onshore movement is the finer stuff, the finer fraction of sediments moving in the bed load. And so we can't predict those changes using fall speed because the bed load isn't being suspended, it's rolling around the bottom. So future research is being directed at creating a way to predict morphologic change from the bed load transport. And I kind of gave you a little bit of a purview of some of the other research using new technologies, drone stuff, to evaluate the morphodynamics of the beaches in Boca and Delray. So with that, I'd like to thank you and thank all the people that go into collecting field research. It's not a one-man band thing. It takes a lot of folks and hands on deck. So these are all the people that were involved in the research I've talked to you about today. So I'm over my time limit with that. Thank you.
Does anyone have any questions?
Questions, raise your hand.
Raise your hand.
The Dix number, the H,
Wave height,
wave height,
Wave
and
height.
the omega is the falling speed,
the fall speed,
and
yes.
the T
Wave
is
period.
the wave period.
Sorry, so yeah, the height of the wave, the time interval between two wave crests, and then how fast the sediment moves. Yes.
When the sea turtle's nest is exposed, does that mean that they die because the sand helps with their process of development?
So I'm learning some biology from my study. I think it depends on the stage of embryonic development. If they make it to a certain stage, then they might still survive unless obviously the eggs crash. But from my understanding, that's all bad. They get exposed, that it's pretty much
They're supposed to be hidden in the
game
sand.
over, yeah.
Yeah.
Yeah, being buried is very helpful for their entire development. So I think they could survive, but probability is no.
Yeah.
Which is sad, right? We like sea turtles.
Yeah, they're cute.